Hello everybody, this is our Desmos Lab that we're doing in place of class last Monday. So what we're starting here with is just a picture of this blue shaded region, and it's a strange shape because it's the area underneath this sine function, sine 2x plus 1/2 x. So we're looking at this sine function and we're supposed to come up with what's the area underneath this curve between these two numbers a and b. Okay, and so a could be not exactly at the origin. I'm just saying a and b could be any two numbers here. So we're just trying to find the area between the x-axis in this curve. Okay, and it's some obscure shape, something that we don't have an area formula for, like area equals length times width, or area equals 1/2 base times height, or pi r squared. The formulas that we know. We don't necessarily have a formula for this. Right? Well, right now we don't. So we're going to try to come up with what could be a formula for this. So looking ahead, let's look at the second slide. What I ask you to do is to draw something. What do you think that we were going to do? And I've noticed some of you that have done it already drew like triangles in here. Some of you drew like this would be a trapezoid, and you drew a trapezoid in here to be the thing that we're going to find the area of. And then some hit the nail on the head when you use rectangles. So what we're going to do here is use rectangles to come up with the area of these obscure figures. So the way it's going to work, I'm going to use this line tool, is we're going to start off with a finite number of rectangles. Like I'm going to use 4. So 1, 2, 3, and 4. And I'm going to say that these rectangles are the height. All right, these rectangles' area is the area. Now you notice some of them are drastic overestimates, like these two over here on the rightmost ones. These are big time overestimates because we're including all this space that's not part of it. And then we have some that are underestimates, like this is obviously way less than what we have. Okay. Now notice what we have here. We have 4 evenly spaced rectangles. So they're the gap between or the base, if you want to call it base times height, is the same for all of them. All right, and the height, if you notice, every time the height of these rectangles is determined by where the rightmost side down here on the bottom hits. So in this case, it's the height at 1, the height at 2, the height at 3, the height at 4. All right, so let me give you that's what we're going to be doing. So if you sketched other figures, that's not a big deal. Don't go back and change it. But we're going to start off with using rectangles. Okay. So here's a visualization of the method. So we start off with one rectangle. N is how many rectangles we have. A and B are still what they were before. They're the left and rightmost point that we are referring to here, where we're finding the area under the sine curve here that we're talking about, the same sine curve between these two x values. Okay. Now n is the number of rectangles we have. Now watch what happens when I make n go up. I get 2 rectangles, and again they're still being the height of them are still determined by the right hand side, the rightmost point on the curve in the rectangle. So if I drag B down, notice that rectangle's height is being determined by B, basically, right? And the size of the rectangle shift because the area that we're determining is shrinking. So the 2 rectangles shrink. All right, and then if I increase the number of rectangles, so there's 3, there's 4, the rectangle's width shrinks down, but we don't have the big errors that we had before. Like we're including all this space that's not included before. But now we're not including so much that we were including before. Okay, and every time we get a little bit better, we're not we're not exactly right on all of them by any means, and really not any of them, but it gets better. Every time we increase the number of rectangles, we get a better approximation. And so the idea is that we are going to make the rectangles smaller and smaller and smaller until they're virtually infinitesimally small, meaning that there's no width down here. That's what we're eventually going to do. Now, what's going to happen if I have no width? How many rectangles can I fit in? Well, when I had a width of 4, I only could fit 1. And then when I had a width of 2, I could fit 2. And then when I had a width of 1, I could fit 4, and so on. So what's going to happen is, as we make these rectangles skinnier and skinnier and skinnier, it's going to need more and more and more rectangles, that's what n represents, to fill up the entire distance between A and B, our starting point and our stopping point. Okay, now C down here, what C just represents, this is just if we're going to use the right corner of the width down here, the 0 or the half. Which one am I going to use, 0 or a half? If it's set to 1, I'm using the 1/2, the number on the right. Okay. If it's set to 0, I'm using the number on the left. Now, the number on the left is 0, so the height is 0. Here, the number on the left is a half between these two, a half and 1. I'm using a half, right? Between 1.5 and 2, I'm using the 1.5. Okay, I'm using the leftmost value to determine the height for the rectangles. Now, I do have another setting here. If I set it to a half, notice now I'm using the midpoint. I'm using the number in the middle of these two. So between 0 and a half is 2.25, and the height at 2.25 is this number right here. So it's just a little bit higher than half, so like 0.6. And that's what I'm using, the midpoints, when I have this thing set to a half. So that's the 3 methods that we have: the left end method, the right end method, and the midpoint method. Okay. Notice when we have right end method, if I have like a polynomial or a trig function, the right end method, we are either going to be an overestimate or an underestimate for virtually all of these. All right. When we have the left end point method, same thing. But when I have the midpoint method, notice every single one, there's a little bit above the rectangle and there's a little bit below the rectangle virtually everywhere. Now there's a turning point right there in the middle of that one, so it's it got a little bit below on both sides. But virtually all the rest of them, we're getting a little bit of an overestimate here and an underestimate here. And what we're going to find out is, you might think they kind of wipe each other out and make it a pretty good overall estimate for the area. Okay, so that's what we're going to be doing here. We're going to be taking these rectangles and filling in based on the height of the function at some point, either left, middle, or right within the interval. This is called a Riemann sum. And what we're eventually going to do is take a limit. We're going to take the limit as the size of the rectangle, the width of the rectangle, shrinks down to 0, or you can also think of it as the number of rectangles needed goes to infinity. So it's another limit. We're back to limits again. So we're trying to estimate the area under the curve, but we're using a limit to do that. An infinite sum of rectangles that are have virtually no width is basically what we're going to do here to estimate this area. And notice when we start off, I'm going to come down here and pause it. When we start off, this was 8. This was the same one that we came off from last time without the dashes in the middle. But we don't have that good of an estimation. But once we start getting a lot underneath here, that overestimation and underestimation, you can hardly see it. And then when we start to get up to a really high number, you really can't see it. So this becomes a very good approximation when we start using hundreds and hundreds of teeny tiny rectangles, teeny tiny width rectangles under here. Alright, so that's the method of Riemann sums. And the exact area under the curve is going to be a limit as the number of rectangles approaches infinity. Okay, now, the questions that I ask here. So what's changing when we go from 4 to, say, 8 rectangles? So what's changed? So what I'm hoping that you saw here was the thing that changed was the width of the rectangles. So this width was 1, and this width was 1, this width was 1, this width was 1. Alright, and what's happening here, our width half every time. So 0.5, 0.5, 0.5, over and over and over again, all the way across. Okay, so what's changed about the rectangles? Their width. And what's determined the height of the rectangles? In this case, again, if you can see it, it's the right end of those interval of x values. Okay, and you can always tell when you have a right end method because the height of the region that you're talking about on the left hand side, the very first rectangle, is not being used. Okay, so if it's the function sitting here and our rectangle is hitting way up here, this is either a midpoint or right end method, and you can easily go all the way across and see it's a right end. Alright, so this is the right end point that's hitting there in both cases. So this is definitely a right end Riemann sum. Alright, another method now, we're using the left endpoints. You can see there on the function now, this is f of 0 is 0 here. And then when we go up to 8 rectangles again, now we're using the left end method. So I want you to see what it looks like when you use the left end of the available interval of the lower number and the higher number of these two, one on the left and one on the right. If you're using the one on the left to determine the height, that's a left hand Riemann sum. And then finally there's the midpoint method. So there's just freeze frames of them in these images. So we're using the midpoint of the interval of x values. Alright, delta x. So I want to see what you guys can come up with this. Alright, everything you need to come up with it is there. So delta x is a half. Okay, a is 0, b is 4, and there's 8 rectangles. So what you need to come up with is a way to get 1/2 from 0, 4, and 8. Alright, so hopefully it's apparent to you. It's basically the distance between here and here is 4. Okay, so how would I know that that's the distance? What mathematical operation would let me know that that's the distance? And then if I want to take that length of 4 and divide it up into 8 equal rectangles, what mathematical operation would I do there? Okay, so there's just 2 mathematical operations between these to give you delta x. So hopefully it's pretty straightforward, but I just want to see what you come up with if you can derive it on your own. Alright, so this is the Riemann sum formula. So hopefully you've seen it before. If you haven't, that right there, that Greek letter sigma, that's the Greek letter sigma, S-I-G-M-A, that's capital sigma, and it means sum. It means you're adding something up. So what are we adding up? I is our index. I equals 0, so x of 0, that's this value right here, x of 0, and then when it goes, it doesn't tell you what it goes up by. You just assume it goes up by 1. So I equals 0, I equal 1, x of 1, x of 2, x of 3, and then 4 is our n. It's how many rectangles we have. 1, 2, 3, 4. So n is 4. That's how many rectangles there are. N stands for how many rectangles or how many subdivisions. So n, 4 minus 1 would be 3, so that means we stop at x sub 3. So we'd stop there because it's a left-hand sum. Okay, we're using the left-hand side to determine these heights. All right, so sigma means adding. We're adding these up. Now, what's the area of this? Well, the area is delta x. Let me erase this down here. The area is delta x times this height, f of x0. So it's a rectangle, so length times width. So the area of that first rectangle is f of x sub 0 times delta x, length times width. Alright, and then the area of the second is f of x sub 1 times delta x, f of x sub 2 times delta x, f of x sub 3 times delta x. They all have a delta x in common, so I can factor that delta x out, and then I'm just adding up those heights from 0 to 3. Okay, so that's what's happening with a Riemann sum. We can always write it this way. We can always write it with the delta x on the outside, just multiply it once, times the sum of all the heights at where we're, the values that we're going to determine the heights of the rectangles. It's always either going to be the left endpoint, the right endpoint of the intervals, or the midpoints. Alright, so that's the formula. It's important to be able to visualize it, is what I'm saying here on this slide, but it's going to be very, very important for you to be able to do it and come up with the numbers. So right here I've got an image of a spreadsheet. I'll bring up my spreadsheet just to kind of go along with it. And I'm going to put in the same thing, in A, B, and delta x. Alright, and this says 8, 0, 4, and then for delta x, how do I get delta x? Well, delta x is what you came up with on that last slide. So what you're going to do is you're going to type in that formula here, but you've got to have parentheses around the numerator. So I'm assuming that you got the earlier thing right, which I said didn't want to show you because I want you to show me that you could do it, but now that we're here, I've got to kind of assume that you're going to get it. C2 is the value in this cell, which is B. So B minus B2 is the value in this cell, which is A. So B minus A divided by A2 divided by N. So there's the cat's out of the bag. That's their delta x formula. B minus A. Alright, close the parentheses, divide by N. So there's our 0.5, our delta x. Alright, so I just typed it in like that. I clicked on the cells every time it came up and I hit enter. Alright, now, once you have it, all the rest of these slides are showing how to come up with the way that we're going to get it. So I'm just going to show you. You can read through this. I'm just going to show you right quick with this Excel spreadsheet. So I'm going to start right here. A is the first value, so I'm going to start with A, and then I'm going to click equals A, our first starting value, plus delta x. Now I'm going to click delta x, and what it says on the slide is once you click it, you hit F4 on your keyboard, and it'll put those dollar signs around the cell that you just clicked. Okay, if you don't have the F4 feature on your keyboard, you can just manually go in there and type the dollar signs. So I can get up here now and type anything I want to in there. So if I didn't have the F4 function, I could just click up here and just enter some dollar signs. Alright, now once you've done that, you're going to click back in the cell you just were, right, where it says add D2, and you're just going to turn that cursor from white to black and just drag down until you get to B, which is 4. Right, you just keep going down and it'll just keep adding D2. Notice up here in the formula bar, it's just going down a cell for the first one, but it's always adding D2. Okay, if you ever did not lock this in, if you click equals this plus delta x, but you didn't hit the F4 feature, if you didn't type in the dollar signs, when you go to drag down, it's not gonna change, because it's trying to add, when you drag down, it drags down the first value and the second value. So A4 D2, A5 D3, A6 D4, and there's nothing in D3. There's nothing in D4. So it's just adding nothing. Okay, so you got to make sure that when you go to add this, that you either click and hit F4 or type in the dollar signs. Okay, so click, turn the cursor black, drag down, and we only need to go to 4. All right, now the function value that we're dealing with that sine function. So when we get all that done, we have to type in the sine function that we want. So right here, I'm going to skip go over to the next line right beside the 0. And I'm going to type in our function equals the sine of 2 times x, or 2x. There's my x value. Close that parentheses, plus x over 2. So plus, remember these are x values in this list. So x over 2. Alright, click that, and once again drag down. There are those function values of the sine function. So what I point out is when we're doing a left-hand sum, it's from the very first one to the next to last one. Right? These are determining the rectangle heights. When we do a right-hand sum, we start at the second one and go to the last one. Right? And then if we want midpoints, I'm going to go ahead and make it on the slides, I make it last, but I'm going to go ahead and make the midpoints. For midpoints, you just take the average. So I'm going to click average of 2 at a time. So this f of x value, comma, this f of x value. That's the midpoint, that's the average. And once I click there, I can again drag down. Alright, so this is the average of B4 and B5. This is the average of B5 and B6. This is the average. It's always, the cell is always the average of the one beside it and the one above it. Right? And we're going to run out right there, B11 and B12. Okay, so that's the last midpoint. Now notice there's 8 of these. N is 8. If you count, there's actually 9 numbers. Right? So when we use, like for instance, the left-hand point method, I would use those numbers. I'm using 8 of the 9. Right-hand point method, I'm using 8 of the 9. Right? And then because there are 8 rectangles, there's 8 midpoints of the rectangle, so there's 8 midpoints. Alright, now what's the formula again? Go back and look at your formula. What are we going to do here? We're going to use this formula. We're going to add up all the function values. Right? 8 of the 9 function values, if we're doing left or right, times delta x. So that's what I'm doing right here. I'm going to use for left hand, I'm going to do LH sum. That's going to be equal sum from the left number, the first number to the next to last, and then times delta x. So there's the left hand sum. Okay, and then if I want to use midpoint sum, that's equal to the sum of all these in the middle times delta x. Alright, and then finally the right hand sum. So that's equal, once again, sum. I'm going to start this time at the second one and go all the way down to the end. Times delta x. Always remember to multiply by delta x at the very end. Okay, that's what we're doing right here. Alright, so there's the 3 estimations of the area using 8 rectangles with the left, right, and midpoints. So eventually it's going to walk you through all that so you can kind of follow along. And then it's going to ask you, okay, what's, which one was the best? So this is when I did it before, and this one I did it now. I'm getting the same things. And it says, okay, this is the exact area under the curve. So the exact area, and I'm rounding it because I'm going to type that in. It's going to give me a decimal. Equals 9 minus the cosine of 8 divided by 2. So there's the exact area, 4.57275, and notice this one's closest. Alright, and then I ask, what happens if you average, this one's less than 4.5, this one's more than 4.5. What happens if I average those two? So let's do it. The average of the left-hand sum and the right-hand sum. So not quite the same. Alright, a little bit less than that. A little bit closer. Right? It's actually, sorry, it is really close to this, but they're not exactly the same. Actually, they still look the same. Let me do a little bit more decimal places. See if we can get any difference to show up. 697 still looks pretty much the same. Well, they do look the same. The question is, I thought they were different when I calculated it earlier. The question is going to be, do you think it will always be that way? Do you think they'll always be the same? Is the left-hand sum and the right-hand sum always going to average to the midpoint sum? So I'll pose that question to you, even though I've kind of already given it away, and see what you think. And we'll discuss it in class a little bit next time. So anyway, there's what we're doing. I want you to try to do it with 16 and 32 rectangles. You can use this same sheet if you want to, and just, this is, you can call this one, n equals 8. And then you could do 16 and 32, the same way that we just did. Just that clicking and dragging technique is what I'm hoping that you'll get down from this video.